Hi everyone, it's Mrs. Westmoreland and I'm here to talk about formation of ions. So we know from our discussion of periodic table families that noble gases are chemically inert or unreactive. That's one of their properties. And we also know that it's the arrangement of electrons that provide elements with their chemical and physical properties. And so these noble gases have arrangements of electrons that are chemically stable, meaning they are unlikely to gain or lose or share electrons. And when we examine the electron configuration of the noble gases, we see that these chemically stable noble gases have full S and P sublevels in their valence energy level. And so when we think about how many electrons is that in the valence energy level, if S and P are both full, well, since S can contain 2 electrons and P can contain 6 electrons, that's a total of 8 electrons in the valence energy level of almost all of the noble gases, the exception being helium, since it only has the 1s sublevel. It just has 2 electrons in its valence energy level. So on your handout, you're asked to write the orbital diagram for 3 neutral atoms, neon, magnesium, and fluorine. And so we are connecting this idea of electron arrangement and stability with having S and P sublevels full with what we already know about electron configurations. In particular here, we're looking at the orbital diagrams. So neon, with its atomic number of 10, would have 10 electrons in its electron energy levels as a neutral atom. So the first 2 electrons were in 1s, the second 2 are in 2s, and then the next 6 are in 2p, for a total of 10 electrons. For magnesium, which has an atomic number of 12, it's going to have the same locations of those first 10 electrons, but then the 11th and the 12th electron need to go into the 3s orbital since the level 2 energy level is full. And then finally for fluorine, since it has an atomic number 1 less than neon, it is going to have just 5 electrons in the 2p sublevel instead of the 6 of neon. So the questions that go along with these orbital diagrams are, first of all, which has full S and P sublevel in the valence shell? And you can see that level 2 is the valence shell of neon. And if we look at all of the S and P sublevels in that level 2, neon is full. So as we said, the noble gases, of which neon is one, tend to have full S and P sublevels in their valence shell. The next question asks, which one will be full if it gains 1 electron? So if we look down here at fluorine, fluorine is really close to being full in the S and P sublevel. It has 7 right now in level 2, S and P, and so it would just need to add 1 more or gain 1 more from a different element that it was reacting with to get a full S and P sublevel. And finally, which one would be full if it loses its valence electrons and uses the S and P in the shell underneath? Well, since magnesium's valence shell is level 3 and it has 2 valence electrons in level 3, if it gives away those 2, again to another atom that it's reacting with, then the next level down is level 2, and so it has a full S and P sublevel in level 2. So once these atoms form ions, they actually all have the exact same electron arrangement. So magnesium has not turned into neon. It still has the same number of protons. So it would have its 12 protons, but now it has only 10 electrons by giving 2 away. So it's going to form a cation with a positive 2 charge. Whereas fluorine has gained 1 extra electron. So it still has its 9 protons in the nucleus. But now instead of 9 electrons that it had as a neutral atom, it now has 10 electrons. So it has 1 more electron than it has protons. So it's going to form a -1 ion or an anion. So we can use the electron arrangement of the atoms to sort of predict what they need to do with their electrons to gain or lose them in order to get a full S&P sublevel, which is chemically stable, and to sort of become like a noble gas in their electron arrangement. So to summarize, and you have a place to do this on your handout, why do atoms gain electrons? Well, they gain electrons when they kind of already have quite a few electrons in their S&P valence shell. So they're going to fill up that S&P valence shell, and then they become like a noble gas in their electron arrangement. And that also makes them more chemically stable. And on the other hand, why do atoms lose electrons? Well, when they get rid of those electrons in the valence shell, and usually it's just a few electrons in the valence shell that they're getting rid of, then the shell below will have full S&P sublevels, and therefore that ion now has a noble gas arrangement of their electrons, and it makes it more chemically stable. So here's a couple examples that should help you fill out the table on the next page of your notes. So rather than write out the entire electron configuration, we can sort of think about how many valence electrons an atom has, how many it either needs to lose or gain to either reveal that full shell underneath or fill up the valence shell. And then based on the change in the number of electrons, the new number of electrons that is different from the number in the neutral atom, we can figure out the charge of the ion that is formed. So electron losers, which are metals, which have relatively small numbers of valence electrons, are going to get rid of all of their valence electrons. And so when we look at potassium and we locate potassium in group 1 of the periodic table, it's a metal. It would be a loser of electrons. So in a neutral atom of potassium, which has an atomic number of 19, it would have 19 protons and 19 electrons. So we don't have to write out the full electron configuration for potassium. We can simply use the periodic table, that is, image is found in your handout, as a shortcut to know that group 1, all of the atoms in group 1 will have 1 valence electron. So since it has 1 valence electron, we know that it's going to lose or get rid of that 1 electron. It's going to give it away to a different atom. So in order to figure out how many electrons are left, I would subtract that 1 valence electron from the original number of electrons in the neutral atom. So B minus C will get me D when it is a loser of electrons. So originally potassium had 19 electrons in the neutral atom. It has 1 valence electron that it gives away, and so I'm left with 18 electrons once it forms the ion. So once it goes down an energy level, it now has 18 electrons. So since it has gotten rid of a negatively charged particle, it has more protons now than it has electrons. So it has not changed the number of protons. Potassium still has 19 protons in its nucleus, but now it only has 18 electrons in its electron energy levels. And so 1 more proton than it has electrons makes it a positively charged cation, with a charge of +1, 1 extra proton. When we're talking about gainers, which are the nonmetals with relatively large numbers of valence electrons to start with, then we have to treat this sort of mathematical approach a little bit differently. So looking at sulfur, sulfur is on the right-hand side of the periodic table in the nonmetal section. It is a gainer of electrons. In a neutral atom of sulfur, it has 16 protons and 16 electrons because its atomic number is 16. Because it is in group 16 of the periodic table, we can take a shortcut and know that group 16 elements have 6 valence electrons. Their electron configuration would end in S2P4 for a total of 6 valence electrons. Since the ideal number is 8 to become like a noble gas, that means sulfur needs 2 more to get to 8. So we need to figure out for gainers how many more electrons the atom needs to get to 8, and then we add that number to the original number of electrons in the neutral atom. So sulfur started with 16, it needs 2 more to get to 8 in that valence shell. And so once it gets that 2 more, now it has a total of 18 electrons in all of its energy levels once it forms the ion. And again, now we're looking at the difference between the number of protons and the number of electrons in the ion. So 16 protons, 16 positively charged particles, and 18 electrons, 18 negatively charged particles. The net charge on this anion that has formed is going to be -2 because of the 2 extra electrons. So use this information to complete the rest of that table, and we will talk more about how anions and cations combine to make ionic compounds in our next class. Thank you.